Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone, and thank you for joining our session today for the AI ML in 5G Challenge finale. The AI and ML in 5G Challenge is a challenge annually hosted by AI for Good from the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. The Machine Learning 5G Challenge is now in its 5th year and aims to create a community to solve network-related problems using machine learning. It connects participants from students to professionals from more than 100 countries, with industry and academia solving real-world problems together. The title for today's session is Beam-Level Traffic Forecasting and Site-Specific Radio Propagation Loss. We will have presentations for the winners for 2 problem statements. First, we'll have the presentations for site-specific radio propagation loss, and then for spatial-temporal beam-level traffic forecasting. Each section will start with an introduction of the problem statement and the presentation by the host, and then it will be followed by each team presentation, which after each presentation will be a Q&A session. It will be at this moment that the audience can ask questions freely using the chat and the video wall, so we are counting on you, the participants, to help create an engaging discussion. Once the presentations for both problem statements are finished, we will conclude with an award ceremony before closing the session today. My name is Mia Nishio from the Nakawa Research Laboratory from the University of Tokyo, and I will be hosting today's session. So without further ado, I'd like to introduce today's first speaker from KDDI, Kazuki Takezawa. If you could explain this year's problem statement, the floor is yours.
Thank you. Okay, I will share the screen. Please wait a moment. This one. Okay, can you see the slide?
Yes, we can. Thanks.
Thank you. So, again, thank you for introduction. I'm Kazuki Takezawa from KDDI Research. Now, let me explain about the content of the task and the results. So, this is page 2. Here's the agenda for this presentation. First, I will introduce KDDI Research and IEIC Rising as the management of this program. And in addition, XGMF and the TTC in Japan support this program. Thank you very much. Next, I will explain the challenge program. After that, I will explain about the schedule of this program and evaluation criteria and evaluation results. So, introduction to KDDI Research. KDDI Research is the research and development institution of KDDI. KDDI is a leading telecommunications company in Japan, offering a wide range of services, including mobile and fixed communications, data-driven services, generative AI, digital transformation, finance, and energy. A company's fundamental research and technology verification in cutting-edge technology spans 6 key areas, shown in the lower right image, that have broad impact on society. Then next, I would like to introduce IEIC Rising. It is a study group that crosses various fields of communication technology. Its mission is to introduce the discuss research finding in intelligent communications technology and system with a focus on AI. It also provides networking opportunity, creating new collaborative relationship between industry and academia. By 2023, it has provided 10 programs in collaboration with KDDI, WikiDDI, and NEC, receiving registration from 181 teams worldwide and submission from 39 teams. Then for this year, in 2024, IIS Analyzing and Wikipedia Research provided programs for these challenges. And next, let's discuss the background of this program. In order to provide stable mobile communication to users, it is necessary to consider factors such as positioning and orientation of antennas. For this purpose, understanding the site-specific radio receiving and condition is crucial. These reception conditions vary from place to place due to the influence of the environment, such as buildings and so on, and can be understood by knowing the radio wave propagation loss. For instance, as shown in the image below, the blue line shows the wave reaching the device directly when the base station emitting radio waves is directly visible to users. In such line of sight environments, the propagation loss changes with the distance from the base station to users. On the other hand, as indicated by orange line, when the base station is not directly visible, radio waves reach through reflections and diffraction by surrounding environments such as buildings. Here, diffraction means a phenomenon going around the structures. And loss, and non-line of sight environments, radio wave reach through various passes, and the propagation loss changes diversely from place to place. Then next, let's discuss the AI model used to solve this challenge. AI is being utilized to accurately estimate site-specific propagation loss, which varies significantly due to surrounding environments. So far, methods have been considered that learn from environmental information extracted from map data and separate propagation loss data, aiming to estimate propagation loss more accurately. Then, next page, continuing, I will explain the consideration the participants were asked to make and include constructing the AI model for radio wave propagation loss. Participants were asked to consider these three core elements. The first one is characteristic to environment. The second one is parameter extraction method. And finally, third one, learning model, AI model. First, for number one, characteristic to environment used for parameter, for example. Understanding the height of buildings between the radio waves transmission and receiving points could provide insights into how much line of sight is available. And they were asked to consider such environmental features that might correlate with propagation loss. Then for number two, parameter extraction method, for instance, quantifying the height of building between the transmission and receiving points at regular intervals of a few meters. They were asked to consider how to extract the process, the features identified in for one and for learning in the AI model, including how they might be represented as images. And then finally, for number three, learning model, they were asked to consider which AI model and structure to use for estimation. And next, I will explain the challenge provided in this program using 3D map data of Tokyo, Ginza, and propagation loss data from multiple transmission points. Participants were asked to estimate the propagation loss from different transmission points. The task was divided into three frequency band categories: 800 MHz and 7 GHz and 28 GHz. The higher the frequency, or the more strongly it is affected by surrounding environment, which increases the difficulty of estimation. Page 9. Next is the schedule for this program. We provided an explanation of the task in both Japanese and English on September 6th. By the deadline of November 1st, we received the registration from 23 teams, and 5 teams submitted their result for the task. And the top performers will present today. And now I will discuss the evaluation criteria. The submission were scored out of 100 points. The scoring criteria were divided into 2 aspects: the usefulness of the AI model and the modeling method. Regarding usefulness, we scored based on the submission points for 3 frequency and their respective accuracy and the variance. Then for modeling method, we scored based on execution, novelty, and complexity. In terms of execution points, we evaluated whether the features, parameters, and AI model they're appropriately contexted based on analysis and research. And next, for novelty, we assess the difference from example provided by us or reference methods. And regardless of the results, how much provided by us, Charlie undertaking. And furthermore, for complexity, we comprehensively score based on the processing time submitted and the estimation method. Then finally, the result of the selection are as follows. The first place MLab, the second place R233 team, in third place CNAI, fourth place SIS Lab, fifth place SHU team 2. And for MLab, we placed the parameter extraction methods and learning model that were solely considered to improve the accuracy and processing volume of the existing methods. Then, the reason of the lowered point, complexity is that LSTM model cannot be parallelized. Then for R233 team, we appreciate the achievement of the highest accuracy of utilizing a pre-trained ResNet model and adjusting parameters with a focus on the convergence of values. Then finally, for CNAI team, we evaluated well the consideration of parameter generation, including FSPL, free space path loss, and the effects of shielding, as well as the AI learning model for these parameters. That's it. Yep. Thank you for listening.
Thank you very much for the explanation. I'd now like to move on to the team presentations. I'm going to first call for team MLab, Diego Soto. So if you could share your screen and start your presentation. As we have 12 minutes per team, you have 8 minutes for your presentation, which will be followed by a 4-minute Q&A session. Once your 6 minutes are up, I will send a chat, so please make sure to finish promptly. We can see your screen. The floor is yours.
Yes, can you see the presentation?
Yes, we can see your presentation.
Okay, let me begin. Hello, everyone. My name is Diego Sato from the Morikawa Naruse Laboratory at the University of Tokyo. It is great honor to be able to speak here today. In this presentation, I will introduce our lightweight and efficient approach to the propagation loss estimation. Our goal is to achieve high accuracy while reducing computational cost compared to traditional methods. Here, we summarize the 3 key innovations introduced in this study. Time series dataset, conversion and LSTM model, and the data augmentation method named TXRX swap. In this presentation, I will first discuss the motivation behind our research, followed by the method we developed, including the dataset, model, and the augmentation technique. Finally, I will present our results, compare them with traditional and deep learning-based methods, and conclude with a discussion on the implementation and on future direction of this work. As shown on this slide, propagation loss estimation often involves a trade-off between accuracy and computational cost. Traditional methods like ray tracing are accurate but computationally expensive, while simpler methods such as the Okumura-Hata propagation model lack precision. Our approach bridges this gap by leveraging sequential data and lightweight neural networks. Many machine learning methods have been used for radio propagation prediction, often relying on image recognition models like CNN and ResNet. Like these approaches, we adopted a time series model to better match the sequential nature of radio propagation from roughly TX to RX. This allows the model to capture key effects such as reflection and scattering more effectively. When building the dataset as well, we focused on cost efficiency. Some previous studies used 3D mesh maps or point cloud data, but these methods are costly. We instead used only height information from 2D maps. This approach simplifies the dataset while maintaining scalability and capturing essential propagation characteristic. Let us now present the method we used, including the structure of our dataset and the design of our model and the implementation of TXRX swap. Each of these steps is critical for achieving the goal of study. On this slide, you can see how we structured the dataset. The TXRX path was divided into 5-meter intervals with 20-meter buffer added at both ends. Height data was collected across 200-meter wide area and transformed into sequential segments. This approach effectively captures the propagation path while minimizing computational overhead. Here, we outline the architecture of our model. It combines 1D convolution for width-wise feature extraction and bidirectional LSTM to process data forward and backward. By minimizing the number of parameters and layers, as shown, we maintained a lightweight design without sacrificing accuracy. This slide shows TXRX swap data augmentation method. By reversing the role of TX and RX, as illustrated here, we double the training data without requiring additional simulations. This method was particularly effective in addressing the limited number of TX positions in our dataset, because we had only 3 TX positions in this dataset. Here, we summarize the experiment conditions under which the model was trained. The experiment was conducted across 3 frequencies band, 800 megahertz, 7 gigahertz, and 28 gigahertz, using the dataset described earlier. The model was trained for 60 approach, and the results were evaluated based on RMSE. These conditions provided a basis for comparing our approach with traditional and deep learning-based models. Let me move on to the results. This slide shows the performance of our proposed model across all frequencies. The RMSE value indicates strong performance, particularly at lower frequencies where propagation is smoother. While some limitations were observed at lower TX height, these results demonstrate the model's ability to generalize well. Propagation models, such as Okumura-Hata model and 3GPP urban macro model. The table shows significant RMSE reduction, especially at higher frequencies, where reflections scattering prominent. This highlights the advantage of using sequential data and detailed training information. Here, we summarize the comparison with ResNet 50. As shown in the table, our model was 50 times smaller and trained 22% faster and achieved higher accuracy. These results demonstrate its practicality for large-scale applications. This slide shows the result of controlled experiments. The table highlights the individual contribution of bidirectional LSTM and TXRX swap, with bidirectional LSTM improving accuracy at higher frequencies and TXRX swap providing consistent improvement by increasing data diversity across all frequencies. As we have shown, this study demonstrates that time series dataset combined with bidirectional LSTM and TXR swap enables lightweight yet highly accurate model for propagation loss prediction. However, future work should focus on testing diverse dataset and addressing limitations like the fixed RX height in our current setup. In conclusion, our CNN LSTM model achieved high accuracy with low computational cost, outperforming traditional propagation model and ResNet 50. TXRX swap enhances data diversity effectively, further improving performance. This approach represents a practical and scalable solution for wireless network design. Thank you for your attention. I will be happy to answer any question you may have.
Thank you very much for your presentation. I'd like to now go on to the Q&A session. If we could get questions from the judges and also from the audience. Okay, I will ask a question. Sorry, my audio cut off very briefly for a second, so I wasn't able to follow your entire presentation, so my apologies if you've already explained it. But were there any other tries or anything else that you wanted to do that you maybe started doing and saw an effort in? I know, or I heard very briefly that you had some future considerations, but was there anything that you tried to do but didn't have enough time or didn't work out?
Sorry, can you repeat the question?
Yeah. Yes. So I know you mentioned some future considerations. Was there anything that you actually tried doing, but you didn't have enough time to complete?
We tried panorama dataset. We mentioned it costs very high, and we tried, but we can't make use of the panorama information. So we think it improves to some extent the performance, but it was very cost expensive. So we didn't couldn't try. We couldn't use this.
Okay, thank you very much. Could I maybe call for Vishnu for a question?
Thank you, Mia. I don't have a question, but I have a very good comment here. I mean, thank you for bringing out the last part. That is, you mentioned about the proposed models and comparison to traditional propagation models. I think these are very important inputs. I think it was slide 15 or so in your slides. This gives us some directions on how the data set could evolve in future. The next data sets could be revolving around or evolving in this manner. So this kind of feedback is very good for us. In slide 15, you have a set of points which explains that discussion on future directions and data sets. Thank you very much.
Thank you very much, Vishnu, for your comment. And with that, I'd like to conclude your presentation. Thank you very much, Hugo, again for your presentation on your solution for this problem statement. I'd next like to call for Zijing Lu to start your presentation.
Okay. Can you see the screen?
Not yet. We can now.
Oh, okay.
Yes. Thank you.
Then can I start my presentation?
Yes.
Okay. Thank you. Hello, everyone. Today I'm great honor to be here to share with you our team's work on estimation of site-specific radio propagation loss. Our team is from Shanghai University, with me as the team leader and Taowen, Shiyimu, Xinyi Wu, Wenjing Xie as team members. Next, I will introduce the 4 aspects of the experimental methodology, model design, experimental results, and some of our reflections on dealing with the radio propagation loss problem. Radio propagation loss is a key issue in wireless communications. It directly affects the quality and coverage of communication, and a current propagation loss estimation is critical for network planning and optimization. Our goal is to construct an efficient and accurate AI model that can accurately estimate the radio propagation loss in a site-specific environment. We conduct experiments in 3 frequency bands, 800 MHz, 7 GHz, and 28 GHz, and evaluate the estimation accuracy and generalization performance of the model. Our experimental results focus on 2 aspects, estimation accuracy and generalization performance. We calculated the RMSE for each band through cross-validation and counted the average of the dB values. The relevant results are demonstrated in the table. And this data shows that our model exhibits high estimation accuracy under different frequency bands, while the variance of the dB values is small, indicating that the model has good stability. In addition, the variance of RMSE and dB values show that our model performs more consistently on different cross-validation sets, indicating that the model has better generalization performance. This graph is a visualized image comparison of the true and predicted values of the propagation loss. From blue to yellow indicates a gradual increase in the propagation loss. The experimental methodology is described next. Our method is mainly divided into the following parts. The first is environment description and data extraction. We use a 3D model of the city and transform it into a 2D height map. This approach preserves the environment information non-destructively, while greatly simplifying the data processing process. We use a Z-buffer algorithm to extract the top-down height information and generate the map. Next is input feature extraction. In order to better reflect the relative position and scale between Tx and Rx, as well as the influence of environmental factors, we generate the input features through the following operations. One is to segment the complete depth maps and locate Tx and Rx at 1/4 point of the median line respectively. This operation can well characterize the relative positional relationship of Tx-Rx and the surrounding environment information. Then we get the propagation distance map based on the absolute distance between Tx and Rx. Secondly, the relative height map is generated. Since one absolute height map cannot reflect the absolute height difference of Tx-Rx, we obtain 2 relative height maps by subtracting the heights of Tx and Rx from the local absolute heights respectively. The size of the above 3 maps are 80 multiplied 80, and finally, these 3 images are used as input. Then comes the normalization of the propagation loss. In order to accelerate the convergence of the network, we normalized the propagation loss. Statistically, we found that the propagation loss values are distributed between 0 and 250. So we divided the target value by 250 to make it distributed in the range of 0 to 1. In the model design, we adhere to the principle of simplifying the structure and remaining the key features, and use ResNet 50 as a backbone network to extract high-dimensional features. A simple fully connected network is used to complete the mapping from high-dimensional features to target values. Specifically, it includes linear layers, ReLU Application Functions Act. This design is simple and efficient and can well handle the mapping problem from high-dimensional to low-dimensional. In constructing the AI-based propagation loss estimation model, we focus on the following points. The first is feature extraction. Key features such as relative position between Tx and Rx, environmental information, and so on should be retained as much as possible. The second is model design. We choose a simple but efficient network structure to avoid overcomplicated models leading to overfitting. The last is the normalization strategy. The stability and the convergence speed of the network are improved by appropriate normalization. In addition, we also found during the experiment that the use of the height map can retain the environment information well, which provides a good basis for propagation loss modeling. As well as the simplified network structure is able to balance the efficiency and the accuracy when dealing with high-dimensional to low-dimensional mapping. This is some of the literature we referenced during the computation. Finally, our experiments were completed in the following hardware and software environments. The training time of the final model is 3.5 hours, and each inference step takes about 0.7364 seconds. Through this computation, we verify the feasibility and the efficiency of the AI-based propagation loss estimation model. Our model is able to estimate the propagation loss stably under different frequency bands, and its estimation accuracy and the generalization ability perform well. In the future, we plan to further optimize the model structure and explore more complex environmental scenarios. Thank you very much for listening to our presentation. If you have any questions, we are very happy to communicate.
Thank you very much for your presentation. I think you covered a lot of sort of questions that I might have had. I guess one that maybe is a little bit off the topic, but could you maybe explain your reasoning behind choosing ResNet 50 for your backbone? Were there any other models that you considered that maybe might change the processing time, for example, or?
Actually speaking, we didn't try other models, but if we have more time, we might try to use the visual transformer network to extract global and local information in the TX and RX environment maps in order to make the network adaptively focus on the environment regions that have a greater impact on the propagation loss through the attention mechanism.
Okay. And were there any sort of considerations you made on decreasing, for example, processing time?
Can you repeat it?
Did you try anything else to, for example, decrease processing time? Just if you have any.
Yeah.
Did you see differences in the processing time, for example, when you tried out different methods?
Not yet.
All right. Thank you. I'd like to pass on maybe to the judges if anyone has a question. Audience as well. Always welcome to take questions. If not, I'd like to pass on to Vishnu for a question or a comment.
I just maybe the Z buffer conversion from, I think it was used to 3D to 2D conversion. That are there some baseline references, and what is the impact of doing that in the performance of the model? Maybe that this is interesting technique. That's why I'm asking the 3D to 2D height map conversion that you have done. Maybe if you give some references, and maybe it's to study the impact of that technique in the overall performance model. That'll be good. Thank you.
Thank you very much for your comment, Vishnu. And thank you very much, Zitin Lu, for your presentation. I now like to call, last but not least, for Gary Lee and Ernest Kernion for your presentation for this problem statement.
Hello, everyone. It's a pleasure to be here to share about our submission to the site-specific propagation loss estimation problem. My name is Gary, and together with Jia, Ernest, Derek, and Peng Hui, we make up the team Communications and Network with AI, and this is our submission. So the next slide with the table summarizes our different methodologies and approaches into this problem, and you can see with varying degrees of success. And in this presentation, we are not just sharing one particular method, but what we hope to do is to showcase the different methodologies, the different insights that we got along the way, and to really shed some light as to how we tackled this propagation loss estimation problem. Chiefly, it kind of ends up in two sets of methods that we attempted. One is the iterated hybrid net, which actually we see some occasional improvements, but yet a few situations where we get significantly worse performance, probably due to severe overfitting. And finally, our final submission is this UNet L3 with kernel-based methods, which we will explain more in a bit. So as I mentioned, the methodology briefly corresponds to one of two architectures that we have explored. And our methodology and approach to this problem actually follows this general three-step strategy. The first is data processing, where we take the information that we have and convert it to a certain representation, a certain way that's more amenable to a neural network model that we can train, and providing additional features along the way as well. And the second step is feature engineering. How do we introduce some transformations or some operations that will make the input much more easily to be processed to be helpful for the training pipeline? And finally, in terms of training a deep neural network, there are also various other considerations, from the architectures to how to train the data to parameters and even the loss function choices that we explore in this submission. So in terms of data processing and input representation, there are a few considerations here. First, of course, is to represent that 3D representation of a city in a height map, and that's what we went along with. But what we also realize is that many neural architectures are generally translational equivariant, but they're not rotational equivariant or invariant. In other words, different rotations might not be, the neural networks might not be as effective to different rotations. But yet in our test cases, given the different positions of Rx for a given Tx, there would be different rotations corresponding to these different relative positions. And so one of the pre-processing steps that we opted to do is to rotate the window that we are looking into such that the Rx to Tx is oriented in the upwards direction, and that fixes that rotational invariance that will hopefully help with the training process through this pre-processing. And for the UNet approach, what we were thinking of was, were there any other additional streams of data of inputs that we can provide to the neural network to learn from such rich features? And so beyond the height map itself, we also took a few different features. Firstly, free space path loss, which is the path loss if we had assumed that there is no interference, no blockages at all. And this gives a good initial estimate, even though a naive and really poor one, it can provide as maybe additional information to the model itself. And the second piece of information that we also included is kind of like a shortest path computation. Think of it as if I have my transmitter to receiver positions, how far are they while walking around the blockages, around the corners. And we computed that distance, which also gives another data point, another set of information that could potentially shed some light as to what's the path that the RF wave signal have to take in order to reach from the Rx to Tx, accounting for the blockages. So this forms our multi-channel input representation to the UNet that we've subsequently trained. And this really summarizes the training pipeline and the architectures that we adopted. So we used UNet, which is really traditionally used in many of the physics-based learning-based methods with the inputs of the multiple channels that I've mentioned earlier on. But an additional thing that we thought of exploring was the loss function itself. We could, of course, just take the inputs and then train the estimated propagation loss of that particular point of interest. But rather than just doing that end-to-end training, it would be also perhaps helpful to train and fit towards the neighboring points as well. And this is where we propose another training loss here, which introduces this kernel. And this kernel is one in the middle, and it decreases along the way. And what effectively it's attempting to do is to fit the estimation of kind of like a approximately 3x3 grid in the middle. So rather than just a single point, it also tries to estimate and fit the neighbors as well. Of course, there are different hyperparameters to be explored, and we found empirically that this 3x3 grid, 3x3 window actually gave the best performance. And of course, if as the kernel approaches to just a single spike in the middle, that corresponds to the point-wise MSE. So this particular approach, notably, actually confers improvements, especially in the hard case of the 28 gigahertz. And of course, the larger the kernel, actually, there's more fitting that needs to be done, and actually what leads to worse prediction result. The other thing that we noticed was, or the other thing that we explored was with the hybrid net. And in this case, actually, if we went with the original set of data that we did, we realized really quickly that it was overfitting and not performing very well. And this is an interesting problem. We did not encounter it in the UNet, but it happened in this hybrid net, which I'll show the architecture in a bit. And so the next line of thought was, what kind of data augmentation could we do? And something that we explored was actually to, after doing that orientation alignment, to also introduce different rotations. And by doing so, what we are trying to fit in this model is not just specific to a particular view of the neighborhood of the city, but to hopefully be able to capture different physics of different building orientations and augment that data set. And this was the main choice that was used for the hybrid net approach. And when I say hybrid net, what effectively it was is the use of a convolutional neural network block that takes in this 2D representation of the heights, of course, with different rotations, and a fully connected neural network block that takes scalars, information like the longitude, latitude, distance, and free space path loss of that particular point as scalars into the network. And then we pass it through hidden layers and concatenate that, and then finally output a final estimate. And in this case, it gives us a certain performance. We reported it under the vanilla hybrid net. But the next thought was that, could we use that initial estimate that might be good, but still not good enough, and put it through a second round of training to a second model altogether, and retrain that? So now using this initial estimate and appending it as another channel to the input and training another model end-to-end in a similar format. And what we realized is that actually we can get some slight improvement gains by doing this stacked approach. But what we also realized are a few challenges. One, there is the hyperparameters of how many iterations we take. And by doing more than once, actually, we start to see deterioration in performance. And the other key thing is that, as you have seen earlier on, as we have reported earlier, there are also certain scenarios where this approach actually led to overfitting and severe deterioration in performance, despite promising improvements in some of the other scenarios. So with that, we opted for the UNet L3 kernel as our final submission. And this plot kind of shows beyond the estimation in errors, kind of like the distribution of how well we are doing or how poorly we are doing at different points relative to the TX position. And what we also start to see is there are, for instance, cases of overestimation of path loss in the corner in the TX1 test cases, as well as the impact of buildings seemingly underestimated in TX3 test cases. So with this summarizes our approach, our methodology to the problem, and these are references. And if you have any questions, feel free to reach out to us. Thank you.
Thank you very much for the presentation. I think we'll have a very quick Q&A session. Ernest, okay, I see you. Vishnu, any comments or questions?
Thank you, Mia. I think maybe just a comment on the type of analysis. It is very structured analysis, so it really helps us to understand the thought process which is used. I believe the question about the analysis about the loss functions and the different architectures. So first one, the UNet and the hybrid, both are quite insightful for us, and also the study of mobility. It appears, maybe I did not get it correctly, but maybe the type of mobility analysis which they have done is also quite interesting for us. Overall, it is analysis wise, it looks pretty interesting. The results, I need to maybe see the results once more, but analysis itself is quite interesting. Thank you.
Thank you for the
Okay.
comments, Vishnu.
Thank you very much. And I'd like to close then the session for this first challenge, the site-specific radio propagation loss. Thank you everyone for your presentations. It was incredibly interesting to see all the different solutions that were provided here. I'd now next like to start off with our second problem statement presentations today for spatio-temporal beam level traffic forecasting. I'd like to invite Tarek from Huawei to explain the problem statement and introduce the team. The floor is yours. But we can see your screen, but I think you might be muted.
All right, perfect. Good day, everyone. I'm Tarek, a researcher at Huawei, and it's my pleasure to introduce this challenge finale on spatial temporal beam level traffic forecasting. So within the context of this presentation of this competition, we introduced a new data set in the field of multivariate time series forecasting. And the challenge centers on forecasting traffic throughput volumes within communication networks. And the communication network that we're interested in is a 5G one, where you can have multiple base stations, and each base station houses different cells, and each cell could contain different beams, and these beams are oriented in different directions to serve different users. And within the data set that we provide, we have different modalities that are used to forecast future values of traffic volumes. So we provide high resolution beam level throughput data with precise hourly granularity. Furthermore, the data set, as you mentioned, encompasses not only the traffic volume, but also throughput time, physical resource block utilization, and user count, with the goal of forecasting future traffic patterns. And these different data sets could be treated as different modalities that could aid you to achieve that goal. So we utilize 4 training data sets, comprising, as you mentioned, hourly network performance metrics for 2,880 beams across 30 base stations. And each base station houses 3 cells with 32 beams. And this data spans 5 weeks. And this totals about 10 million data points that the participants can use for training their models. And the target, the forecasting target is 1 test week that is immediate to the training that immediately follows the training set. And another test week that follows the first one after a gap of 4 weeks. Now we established a number of beams and the target time horizon. So the participants are tasked to provide a predicted traffic matrix for the throughput volume. And this is evaluated against the test traffic matrix with this metric, the mean absolute error, evaluated on a target comprising about 1 million points. And that's roughly 10% of the training set over the 2 weeks that we mentioned. So the challenge was live for 2 months, and we got around 700 enrolled participants, and we've identified 5 winners with competitive submissions and also valid code and documentation. And drum roll, please. And these are the winners of the challenge. So we have 5 winners. The first place goes to the person with the handle of Kolesh. The second place goes Kobus Berger. And the third place goes to Sen Drohu. And the fourth place goes to Batuhan. And the fifth place goes to Abdurrahman. Thank you. And I give the token to the participants to present the solution.
Thank you very much, Tarek, for the overview of the problem statement from Huawei. With that, I'd like to now call for our first presentation from Stephen. If you could show your screen and start your presentation. And as mentioned, once your 6 minutes are up, I will let you know that you have 2 more minutes left by chat.
Can you all see my screen?
We can see your screen. Yes.
Cool.
Yes,
so my
please
name
go
is
on.
Stephen. I'm going to introduce my solution. So this presentation explores the challenges of predicting traffic throughput volumes in communication networks, focusing on using advanced machine learning techniques to improve network performance and resource management. So the challenge of beam level traffic forecasting, increasing demand, the rapid expansion of communication networks, and the increasing demand for data traffic pose a significant challenge for network operation and also beam level precision. I'll not talk more about like the background because the Huawei researcher has already talked about it. So my solution was leveraging gradient boosting decision trees. And there was one huge problem to solve because of the forecasting horizon. As explained, the test set consisted of 1 week immediately after the 5 weeks and another one 6 weeks after. So the image on your right, we have the original data sets. The blue points represents the train data. The orange represents the test data. The blank here represents the time gap. So you can see if we create temporal features, for example, lags, we have the lag for week 6, but you don't have lags for week 11. So that was one thing to note. So the dataset overview, we were given throughput volume, throughput time, number of users, physical resource block utilization. My feature engineering techniques. So I used a number of features. So rolling features, expanding features, weekly aggregation features, shifted features, and target encoding. And I'll go in depth of each feature I used. So if you look at this diagram, I solved for each week individually. So we had the original features, for example, hour, base station, cell type, and beam. The daily hour I created for myself because like the hours spanned 168 hours, representing 7 days. So the daily hour is 0 to 23 hours of each day. So for the week 6, the immediate week after the training data, I grouped by base station, the beam, and the cell type, and calculated the rolling statistics. This included the mean, median, standard deviation, and quantiles, computed over 2 window sizes, 168 hours representing 1 week, 336 hours representing 2 weeks, and with a shift period of 168 hours to prevent nonce for some test hours. I also calculated expanding statistics. This included mean and standard deviation, beam level weekly mean. So for each group, the mean target for the previous week was calculated and mapped accordingly. And then I also created shifted features. This included lags plus, for example, the same hour this week. What was the volume? Same hour previous week. And also one of my powerful features was target encoding features. And this is because it could be shared between the 2 weeks. So all the other above features, the rolling, expanding, shifted features, all these temporal features could not be used for week 11 because remember there was this time gap that you are supposed to take into account. So for the target encoded features, I calculated them using folds to prevent target leakage. So this would mimic the train test real life scenario because you don't want your fold to be evaluated with the same target distribution it has. So for week 11, I used the original features, plus I also grouped by base station, beam, and cell type, and also calculated target encoded features the same as week 6. For target encoding, I used a combination of groups. So I used base station, hour, daily hour. Remember, hour is the 0 to 167 hours for the whole week. Daily hour is 0 to 24, 0 to 23, I mean. Then beam, then a combination of base station and all the other categorical features. Then the target columns used, I used the throughput volume, which is the targets, the user counts, and physical resource block utilization. The statistics calculated included the mean, the standard deviations, keyness, minimum, maximum, specific percentiles, like for example, 95 and 0.01. So model training and evaluation. So I used a stratified keyfold with 10 splits, and the models I used were LightGBM and cat boosts, all of them being gradient boosted decision trees for both the time horizons. Then I used feature selection strategies, 2 distinct feature selections, where temporal features are excluded for week 11, but used for week 6. So my training and evaluation pipeline in depth. So my pipeline, I trained individual models for each approach with appropriate feature selection. Approach 1 for week 11 used the features, all features excluding the temporal features like lags, expanded means. Approach 2 used all the features, including the temporal features. Each individual model was used to perform inference on the week mentioned. For example, approach 1 was used for week 11, approach 2 was used for week 6. Models, cat boost and LightGBM. Hyperparameter tuning, I used Optuna. My training results. So LightGBM, so each approach was evaluated individually. So approach 1 had a CV of 0.1971, approach 2, 0.1912, and then cat boost 1.1972, 0.1917. They almost had the same similar scores. So I don't think this ensemble that I created a lot of diversity, to be honest, but it improved my final score. So inference results, the public leaderboard, as from the discussions, people noticed that the public leaderboard was the immediate week, and then the private leaderboard most definitely would have been the week 11, the one with the time gap. So I used this intuition to create my CV and also to evaluate my models. So the public leaderboard had a score of mean absolute error of 0.1925, and the private leaderboard 0.2262. Public leaderboard for cat boost 0.198. Private leaderboard was 0.2262. You can see they had similar scores, and the ensemble 0.1919, and the private leaderboard was 0.2261. So feature importance for week 11, you can see target encoding features ruined. For week 6, rolling features and shifted features. So key takeaways, target encoding effectiveness, feature selection importance, because if you used like temporal features for week 11, you would have experienced massive shakeups that affected a lot of participants. GBTT model sustainability and ensemble models potential, although the ensemble didn't improve the results that much. So I want to thank the host for such an interesting data set. I really enjoyed working on this problem since with the feature selection, my cross-validation was very stable. So when I improved locally, it guaranteed an increase in the LB, and this is a dream for competitive machine learning. Thank you.
Thank you very much for your presentation. Brief question from me. Were there any other sort of future improvements that you wanted to make that you didn't have enough time to do this time around, or yeah?
Yeah, sure. So I wanted to try PyTorch temporal fusion transformer, but I never had enough compute, so I only resorted to using gradient boosting decision trees.
Okay, and you think that would have improved your results even further?
And I'm not really sure.
Not really sure. Okay, thank you very much. Vishnu, final comments or questions?
Time horizons. I think there were two time horizons. I believe we discussed this in the beginning of the challenge also. The 6 weeks and 1 week time horizons. What are your observations, or what were the steps that you took towards handling both these time horizons?
Yeah, so for week 6, there were 5 weeks historical data. So I could use temporal features, for example, the roll-in means and the roll-in statistics, expanding statistics, and shifted features. But for week 11, then you don't have, like the 5 weeks before, they're all nonce. So there's no way to use temporal features. So I resulted in using only the target encoded features that really improved my score. And I used this for both the week 6 and week 11. Only that for week 11, I excluded all temporal features.
Great. Okay.
Okay, thank you very much, Stephen, for your presentation. I'd now like to next call for Abdurrahim for your presentation, please.
Are you seeing my screen?
Yes, now, yeah.
Okay, thank you. So, hello everyone. My name is Abdurrahman Desalifu, and I'm going to present you the 5-by solution for the spatio-temporal beam traffic forecasting. So yeah, here is the plan of the presentation. I'm going to start with a problem overview, and then I'm going to move to data processing part and feature engineering. And after that, we're going to talk about the modeling and then inference and evaluation and some future consideration. So to start us, the dataset we have been provided contains hourly beam level traffic data for 5 weeks across 30 base stations with 3 cells and 32 beams per base station. And each row in the dataset represents the traffic volume for a given hour, beam, and cell, along with other features like physical resource block utilization and user count. The key feature provided in the dataset is the downlink throughput volume, which is the target variable representing the traffic throughput volume. And we have the physical resource block utilization, which measures the network resource usage, the user count, which is representing the number of active users connected to each beam. And then we have time future, which are provided with hourly granularity data with 20 hours a day and weekly periodicity. So the goal of this challenge is to forecast the beam level traffic throughput volume for 2 target week 6 and then the week 11 using 5 weeks of historical data. And the aim of this is to enable ATU to be able to make efficient resource allocation by being able to predict in advance the traffic throughput volumes, be able to reduce the energy consumption and manage congestion and optimize also the user experience. So for the data processing part, we have started with some data exploration, which enable us to get to understand more about the kind of data we are dealing with. Here you have a traffic variability, which shows some cyclicity in the data set we have. We also calculated like the seasonals and residuals using time series decomposition to have a better understanding of the datasets we have. Our techniques heavily rely on feature engineering in order to boost the performances of the model. We first started with cyclical time-based feature. Traffics in telecommunication follow strong daily and weekly traffic peaks, like during work hours and drop overnight. To capture this pattern, we encoded the time feature we have by using two variables, the hour sign and hour cosine, and we use a flag is weekend to be able to separate whether the weekdays and the weekend. And also we have a feature we created is peak hour to be able to detect the peak hours. For the lag feature, we created a 1 hour lag feature to capture daily repetition in the data. We also created 24-hour lag feature, which gives us the daily variation in the data set. And then we also created a 168-hour lag, which provide us information about a week ago to enable the model to increase its performances. And for the rolling averages and congestion feature, we have created a congestion interaction which use the physical block resource utilization with the number of users connected to the network in order to be able to detect any congestion that may affect the traffic throughput in the beams level. And we also created rolling average 3 hour and 12 hour, which included computing the mean, average, and standard deviation for each of the beam information we have. So for the modeling part, we use a blended approach model which combine a temporal convolutional neural network and a gradient boosting regressor. Yeah, so for a temporal convolutional neural network, it's made of two dilated convolutional layers. The first one has a filters of 64. We use an activation ReLU, and the regularizer is L2 in order to enable the model to prevent overfitting. And we use a residual connection between the two convolutional layers in order to be able to avoid the vanishing gradient problem. And here we use a gated recurrent unit, which enable the model, which is very effective in time series at the return relevant information from previous time step, making them ideal for long range time dependencies. We've also included the multi-head attention in the convolutional neural network architecture to enable the model to focus on specific time points that are most relevant for prediction, enhancing then the model's ability to capture relationship between distance time step and near time steps. For the model configuration, the optimizer we use here is Adam, and the learning rate is 0.001. We train for 100 epoch, and we use a batch size of 62. And for the XGBoost model that has been used to complement the convolutional neural network in order to be able to capture the nonlinear interaction that the main model may have missed, we use like a learning rate of 0.05, a max depth of 3, and the number of estimator is 50. For the hardware configuration used for the training, it's a Kaggle GPU 100, and the training time for both the models is 1 hour and 15 minutes. So for the temporal convolutional neural network, the mean absolute error we get is 190.22, and for the XGBoost validation, the mean absolute error is 111.62. And we decided to blend the two model, and the weights we have, the best weight we get is 0.5, 0.5, and this leads to a private leader score of 0.2286. And yeah, here are the references we use for doing this model. And future work consideration is to combine the feature created with more powerful time series focusing model like lag-llama or temporal fusion transformer. I did not have enough computing resources to use. I've tried implementing the temporal fusion transformer because it's like a state-of-art machine learning model when dealing with time series forecasting. But unfortunately, each time I try, it keeps crashing my kernel. So, and also employing a graph neural network to leverage the spatial interaction across the different beams, which will enable the model to effectively capture some features such as the congestion or interference that may have in neighboring beams. and also to use hyperparameter optimization and residual learning approach. What I mean by residual learning approach is to create a second model that we use the residual from the first model in order to be able to correct the prediction, making the
You have a
model
minute
much
left.
more accurate. Okay, this is it, and thank you for your attention. Stop sharing.
Thank you very, very much for your presentation. Unfortunately, we are slowly running out of time. I'd like to call for Vishnu to make a brief question or comment.
Kaggle GPU. Abdurrahman, thank you very much. This is a really interesting presentation. I want to ask your experience with Kaggle GPU. There are several other questions, but let me ask this one. Kaggle GPUs, you already told that you had crashes when you tried the last approach, but how did it work with your existing approach which you have tried? What is your experience?
Sorry, could you repeat?
Kaggle GPU. You used Kaggle GPU for this?
Yeah, I use Kaggle GPU. I've also sent a request for ITU to get access to GPU, as you have told us that when working with this kind of competition by filling the form, we have the possibility of getting GPU. I have sent 3 emails but didn't get a reply, so I worked with the Kaggle one. And yeah, I think if I have more computing resources, I could have implemented the temporal fusion transformer model to combine it with my actual features in order to increase the precision of the model. Yeah.
It will be truly interesting. Let me talk offline. Thank you very much.
Okay, thank you.
Thank you very much for your presentation. Now I'd like to call for start your presentation.
Okay, I quickly share screen.
Thank you.
Can you see it?
Yes.
Okay, perfect. So my name is Sander Hunziker. I'm a student in environmental engineering from Switzerland, and I'd like to share you my solution for the spatio-temporal beam level traffic forecasting challenge. So as mentioned before, I think the main problem of this challenge was that we had these different forecasting horizons. Once the 6th week and once the 11th week. So I used 2 different approaches for this forecasting horizons. For the 6th week, namely, so this is just a quick overview, I go into more detail. So here I used features based on the traffic throughput volume, which was also the target variable, and like temporal features like the hour and the day, then statistical static features of the volumes, and I used singular spectrum analysis to denoise or to add additional features. And the solution was based on an ensemble of 2 TS mixer models, 2 tidy models, and 2 NHITS models. And then for the 11th week, I used a histogram-based gradient boosting regression tree, which only took temporal features such as hour and week as input. And then I just simply combined the output of the gradient boost with the prediction for the 6th week. So here's an overview of or the method I chose for the 6th week forecast. So as mentioned before, I used some static features where I just calculated some summary statistics per node, cell, and beam, and I calculated the mean and standard deviation. Then I used, as past inputs, I used the target variable itself. So it's an autoregressive model. And I used this singular spectrum analysis to decomposite the input. So as I noticed, the input was quite noisy, and to get like this trend and periodicity features, I used this SSA approach, which is quite fast and Yeah, and it's also non-parametric, so there is nothing to fine-tune, and it's easy to implement. And I applied it over a window of 24 hours, so over one day, and I used the first, so the trend, and the two periodic signals as features. Then, as past and future inputs, I used the hourly mean of our target. So it's just a statistical variable, and day and the hour encoded as a sinus and cosinus wave. And then as an output, I get the total week forecasted. So I used the darts library to implement these models. Like I said, the ensemble consisted of two TS mixer models, which is a state-of-the-art model introduced in 2023, I guess. And here I used two different configurations, one with a hidden size of 32 and 16, so a big and a small one. Then I used these two neural hierarchical interpolation for time series models, these N-hits models, here with different dropout, and two time series dense encoder tidy models, also one big and one small version. And additionally, I use this reversible instance normalization. So this basically scales the inputs, and this is really good to account against internal distribution shifts. So it's a quite powerful technique in time series forecasting. And here are my local results. So I trained the models on 4 weeks. So what you see here is the mean absolute error and the standard deviation of the absolute error. So when I average over all models, I get a local mean absolute error of 0.19. And we see here that each model is worse than the combined performance, but the TS mixer is the best one. And then for the 11th week, I chose a quite simple approach like this. I basically thought it's really difficult to actually forecast the 11th week because we don't have any data to forecast it, or like we can't. So we only had 5 weeks of data and we had to forecast the 11th week, so it was hard. So I basically just thought I use one model which is only based on time features like day and hour, this histogram-based gradient boosting regression. And then I combined this with the prediction of the 6th week because I thought this week is more in the future and more similar to the 11th week. So here I wrote some potential improvements. So the first one is a little bit obvious, but it would be nice to include the additional covariates these mentioned here, and then also to play around a little bit more with the singular spectrum analysis to make a bigger window over the whole week to maybe better capture trends along the week. Then additional hyperparameter tuning, I didn't really tune them. And then as well train the ensemble on all the data available. And for the 11th week, maybe if there's more data available, a better model could be made. Yeah. So thank you very much for listening, and I'm now open to questions.
Thank you very much. I'd like to pass on to Vishnu for some comments or questions.
Sandra, thank you very much. Maybe a quick, out of the line question. How did you get from environmental sciences to this kind of challenges? Are you kind of interested in machine learning challenges in general, or is that kind of side interest, or do you work in this area?
So I think it's really interesting. So it was just my interest to get into machine learning, and I also took courses on machine learning. And I think it's a field which shapes every other, like it shapes every job or industry. So yeah, it's really interesting also to combine machine learning with environmental sciences.
Yeah, I believe your solutions are really interesting. In fact, I was asking the previous participant as well. The time horizon approaches are quite interesting. The way you handle. We perhaps we can chat offline. But there are specific challenges which are problem statements, which are IT problem statements, which are related to environmental sciences itself. If you are interested, you can take a look and we can discuss.
Yeah,
So
it
thank you
would
very
be
much.
really
It's quite
interesting. Thank you.
interesting. Your approach is actually interesting. Thank you.
Thank you very much. In the interest of time, I think we're going to close the presentations there. I'd just like to thank everyone for your presentations. We can see just the amount of effort put into each solution, and we really much thank you for joining this year's AI and ML in 5D Challenge. I'd like to now move on to the awards ceremony. If I could first call for Chimbo-san to announce the winners for the site-specific radio propagation loss problem statement.
Okay, I'll explain the winners. Just wait. Okay, can you see my screen?
Yes, we can see your screen.
Okay, so I'll put this. Just okay?
Yes, we can see your screen.
Okay, so I will explain the winners for our challenge program number 19, estimation of the scientific radio propagation loss. So winners, first place is the team MR, and the second place is the team at 2023, and third place is the team Kianai. So I would like to say thank you for persons to join this program, and I hear you. Thank you.
Thank you very much. Congratulations to all the winners. And I'd now like to ask for Tarek to announce again the winners for the beam level traffic forecasting problem statement.
Again, thank you for the participants for their efforts. And the winners are Kolesh in the first place with the handle Kolesh, and the second place goes to Cobus Berger, and the third place goes to Sandro. Thank you all for the efforts and also your presentations and showing all the innovative approaches to achieve these competitive solutions.
Thank you very much, Tarek. Thank you again to everyone who has joined today's session, and I'd especially like to thank all of our hosts who hosted the problem statements for this year, the winners who made the presentations today, and the judges who joined us. And of course, I thank everyone for joining today's webinar session. It was incredibly interesting to see the different solutions and the different ways that people have gone on to tackle these different real-life problem statements and communication networks. As mentioned, the channel is hosted annually, so we have more sessions planned for the near future. Please check the AI for Good program page for updates. And if anyone has any questions or comments, you can always interact with us or the other participants on this challenge Slack channel. I thank everyone again today for sparing a valuable time to join the finale, and I wish everyone a very lovely rest of the day. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for good.